To begin, we had to decide on which type of ball would be considered our baseline ball. When making this decision, we referenced the articles from class about modifications made to the surface of a sphere to see which would fit best. The papers described the effects of modifications, such as removing mass, and since we would also be making a similar modification, we wanted a ball that had a significant mass so we could alter it in various ways. Initially, we thought a tennis ball or wiffle ball, but both were hollow. Soccer balls and basketballs were too large, and both baseballs and softballs didn't have an ideal drilling surface. Lacrosse balls offered a smooth surface as a baseline and were dense, so we could remove different amounts of mass for the altered versions. The next part was deciding what modifications to make on the baseline ball. Based on the article, Control of Circular Cylinder Flow by the Use of Dimples, dimple modifications have a beneficial effect on the flow. Dimples cause the critical regime to occur at lower Reynolds numbers and cause a reduction in drag. Because of these factors, we made two modified balls, one with shallow surface dimples, evenly spaced across the entire ball, and the other with deeper dimples farther apart. In the previously referenced article, it was stated that only golf ball-like dimples were tested, but other depths and arrangements might be beneficial, so we tried it. Based on the research and articles, our hypothesis was that the dimples would reduce drag and increase the distance that the ball traveled. The next step was testing the three balls that we made. We decided to use a slingshot to launch them and measure the distance traveled on a local football field using the yard markings. This kept the launch as consistent as possible. We had the same two team members hold the two sides of the slingshot up to the same height each time, while another team member pulled it back the same distance to launch. When the ball landed, another team member went from the nearest 5-yard marker and measured how far it had traveled in between those markers, and then added them together to create the total distance. Each ball was launched 5 times, and the average distance was found. The time it took each to land was also recorded. Because of the snow, definitive markings allowed for accurate measurements and for consistent launch, as well as landing points. Although we hadn't anticipated the snow, when we arrived at the football field it was covered, so we cleared paths to find the yard markings until the 90-yard line, and it allowed for accurate measurement of where the ball first landed. Here's an example of the marking the ball made in the snow each time it landed. The ball rolled a significant amount after each launch, but the measurement was made to the first initial contact with the snow and not to where it rolled to. After the experiments were conducted and the averages were calculated, the deep dimpled ball went the farthest, as seen on the graph above.